Today's lesson is on polynomial functions again, but this time we're going to focus on zeros and how to find them. So we will be using what's called the fundamental theorem of algebra and the complete factorization theorem to find some rational zeros of a polynomial function. Then on part 2 of the lesson, we're going to find conjugate pairs of complex zeros. And then we're going to factor and find all the zeros of the polynomial, which could be complex and or real. So the first thing we need to talk about is the fundamental theorem of algebra. And the fundamental theorem of algebra guarantees that in the complex number system, every nth degree polynomial function has precisely n zeros. So the first question there is, how many zeros does the polynomial function this f of x have? Well, it's all dependent on the degree. And since it's a fifth degree, it has 5 zeros. Okay, simple. So using this theorem then, we can figure out what possible zeros can happen in this polynomial. To do that, we can look at the constant term and the leading coefficient. And if we call the constant term a sub 0, if we call that p, the factors p, and then q, the factors of the leading coefficients, and we divide them. Now they can be plus or minus. Should put plus or minus q, p over q here. And this is what we call the rational zeros test. You list all the factors of the constant and all the factors of the leading coefficient. And once you do that, you can figure out what possible zeros there could be. So here's an example. List all the possible rational zeros for f of x, which is q. Well, let's look at the constant. What are the factors of 9? Well, you have 1, 3, and 9. 1 times 9, 3 times 3. That's it. 9 times 1. What are the factors of the leading coefficient 3? Well, 1 and 3. That's it. So now remember, it was p divided by q. This was p, this was q. So p over q then, now they can be plus or minus as well. We could have plus or minus 1. We could have plus or minus, which is 1 over 1, or 3 over 3. We could have plus or minus 3, which would be 3 over 1, or 9 over 3. We could have 1 over 3, plus or minus 1 over 3. 3 over 1, 9 over 1, oh, better get 9 as well. So plus or minus 9. So here, I believe that's it. Those are the possible rational zeros that are in f of x equal 3x cubed minus 19x squared plus 33x minus 9. So now what do we do? What do we do with those? Well, technically now we'll get into the fundamental theorem of algebra here in a little bit and do all those things, but we can look at these and know that our graph is either going to go through 1 or plus or minus 1, plus or minus 3, plus or minus 1/3, or plus or minus 9, or any combination of the 3. It doesn't guarantee that all 3 will be real, or rational, I should say. There might be some complex zeros. But in this case, we at least know what the rational ones could be. Okay, let's look at the second example. Okay, we got a quartic. So we have 4 possible rational zeros. So what are the constant? Well, the factors of the constant, plus or minus, well, we don't need to put plus or minus on these. We can just put 1, 5, and I think 25, and that's it, isn't it? Yeah, that's it. And then 2 is just 1 and 2. So now we list the possible rational zeros. So you have plus or minus 1. Let's see, can we get 2? I don't think we can get 2, can we? I don't think we can. 1 over 2, but we can't get, so I'm going to do, what I like to do is I like to take the P, this is P, remember, and this is Q, and this is P divided by Q, so I like to take 1 over 1, 1 over 2, and then 5 over 1, and 5 over 2, and then 25 over 1, and 25 over 2. And there's all the possible zeros. Now the rational zeros test allows us to find the zeros that we can use in synthetic or long division to reduce the degree of the polynomial to a cubic or a quadratic equation where we can use algebraic techniques that we already know, like factoring or quadratic formula, to find the remaining zeros. So let's find all the real zeros of example 3, okay? What's P? Well, we have 1, 3, and 9. What's Q? 1 and 3. So our possible zeros, P over Q, is going to be plus or minus 1 over 1, plus or minus 1 over 3, plus or minus 3 over 1, plus or minus 3 over 3, but that's just 1, plus or minus 9, and plus or minus 9 over 3, which is just 3. So those are our possible zeros. Now, we can, it's not really cheating, but it is. We know we have 3 zeros. We know it's going to be a cubic, so it's going to be a chair function. We can go ahead and graph it and see if we can find where that would be. Well, it looks like to me, and here's the graph of it, if you use our calculator, it looks like it's going to be at 3. So it looks like plus 3 is a 0. And it also looks like this one could be 1/3, does it not? So those are the things we have to look at. Now we only have 2, so the third one would be a complex 0. So now we got to find them, okay? So how do we do this? Synthetic division, okay? So let's pretend we think it's 3, right? We think it's 3 would be the factor. Is it 3 or is it minus 3? Well, if you remember from synthetic division, is it x minus 3 then? So we bring 3 down, it's negative 9, negative 28. 3 times 28. Oh, it's not negative 3, is it? Must be positive 3. There we go. So 3 times 3 is 9, negative 10, that's negative 30. That's positive 3, and that's positive 9, so 0. So 3 is a 0. 3 is a 0. We just proved it. Now, what's left, because we have a remainder of 0, remember, from the remainder theorem? What's left is 3x squared minus 10x plus 3 equals 0. Now, how do we find the other factor? Well, we can keep going and just do with 1/3, or we can factor it. Since we think 1/3 is one of them, why don't we just use this and see if it works? Okay, let's bring down the 3. 1/3 of 3 is 1, that's negative 9. 1/3 of negative 9 is negative 3. Hey, there we go. So 1/3 is a 0. So the other one, what we have left, is 3x minus 9 equals 0. Well, wait a minute, guys. Did we not catch that this multiple 0 is located at 3? Remember? From 3.2, lesson 3.2, we talked about multiple zeros when we have a bounce right here. When it bounces off the x-axis, it's a quadratic, or it's 2. It's to the second power, it's to the fourth power, etc. But it's an even power. So therefore, we have a multiple 0 of 3, and our other 0 is 1/3. Cool. And there's our 3 zeros. So now, moving on, The complete factorization theorem states that if we know the zeros, then we can find the linear factorization theorem, the model. So we know that there's going to be n linear factors if we have an nth degree polynomial. And then, of course, we have that little constant that stretches it, flips it, or compresses it. So let's find, on example 4, the real zeros, and then let's write the polynomial in factored form. Okay, and notice this says factored, so we don't have to multiply it all out. So, well, it's already multiplied out, sorry. So it looks like -1 might be, and then we have this one we don't know, and then we have that one. Well, what do? Well, we think it's -1, but we don't know. Well, let's do our P over Q quick. So first of all, P is 15, so 1, need to quit putting plus or minus. 1, 3, 5, and 15. Ooh, there's a bunch there. And Q is 1, 2, and 4. So now we can start dividing. We know 1 over 1, 1 over 2, 1 over 4, 3, plus or minus 3, plus or minus 3 over 2, plus or minus 3 over 4, oh boy, plus or minus 5, plus or minus 5 over 1, or 5 over 2, sorry, plus or minus 5/4, plus or minus 15, plus or minus 15 halves, and plus or minus 15/4. So we have a lot of options. Notice -1 is in our possibilities. So should we try it? We might as well. Got nothing to lose. So let's see if -1 synthetically divides and gives us a 0. Could bring 4 down, we get -4. I don't know why I put -x. Sorry about that, that should be -1. So that's going to be -16, add 16, that's 15, -15, 0, we got a 0. So x equal -1 is a 0. Okay, so now we have 4x squared minus 16x plus 15 equals 0. Now how are we going to find those two? Well, it looks like it might be 3/2, 1.5. It's not 3/4. It's not 2.5. Is it 1.25? That's going to be the thing. Is it 5/4? Well, let's go ahead and just keep synthetically dividing. I'm going to guess, and I don't know, honestly. I think it's 3/2. So let's try 3/2. So we have 4, -16, and 15. Bring down the 4. 3/2 of 4 is 6. That's a -10. 3/2 of -10 is -15. Boom. 3/2 is a 0. So we have -1 and 3/2. But it looks like we have a third. So we have 4x minus 10 equals 0. And then we solve for that, and we get 5/2. And there's our zeros. Now it says to write the factored form. Okay. F of x equals, let's see, it'd be x plus 1, x minus 3/2, and x minus 5/2, and call it good. That's a lot of fun, isn't it? I think it is. Okay, example 5 here. We should notice a multiple 0 right there. Looks like that's -1, we think. Here, I don't know. We're going to find out. Let's do our P and Q. Oh, this is easy. 1 and 2 for P. Q's 1 and 3. This is going to be short. So P over Q is plus or minus 1 and plus or minus 1/3, plus or minus 2 and plus or minus 2/3. Those are the only factors that it could be. And it looks like -1 could be a factor. Let's see indeed if it is. And it is. Synthetically divide, we got -1. So x equal -1 is a factor. That other one can't be 1/3. I know, maybe 2/3. Let's see if it's 2/3. 3, 1, and -2. Again, we can factor this if you want, or use the quadratic formula, but I'm not. I'm just going to keep going. 2/3 of 3 is 2. That's 3. 2/3 of 3 is 2. Looks like 2/3 is a 0, but look now closely, guys. If you look close, I know 3x plus 3 equals 0, and I know 3x equal -3 and x equal -1. That makes perfect sense. We got a multiple 0 right here, and we should have right there. So if we're going to write our factors, we'd have x plus 1 quantity squared, and x minus 2/3 would give us this graph and that equation. Number 6. Ooh, boy. This looks like a fun one. Looks like we got a U shape because it's a quartic. So our P is 1 and 2. Our Q is 1, 2, and 3 because it's 6. Factors of 6. So now our P over Q is going to be 1 over 1, 1 over 2, 1 over 3. Oh, I forgot 6, didn't I? And 1 over 6. And then we have 2 over 1. 2 over 2 is 1. 2 over 3. And 2 over 6, which is 1/3 already. And then that's it. So those are our options. Now, it looks like 2 is where we should jump off, doesn't it? So I'm going to go with 2 as my jumping off point. 6, -7, -12, 3, and 2. That's 12, 5. 2 times 5 is 10. That's -2. That's -4. That's -1. -2, 0. X equal 2 is a 0. And that gets us to a cubic. 6x cubed plus 5x squared minus 2x minus 1. That's not very good. But it looks like -1 may be a 0, so let's try it. 6, 5, -2, -1. I'm not sure it is, but we'll check it. -1 times -1 is 1. It is. We got it. X equal -1. So now we're left with 6x squared minus x minus 1 equals 0. And, ooh, it's either 1/2, 1/3, 2/3, or 1/6. I don't really want to factor this, so I'm going to guess that it's 1/2. And if I'm wrong, I'm wrong. And synthetically divide it. 1/2 of 6 is 3. That's 2. 1/2 of 2 is 1. And guess what? It worked. So 1/2 is a 0. That leaves me with 6x plus 2 equals 0. 6x equals -2. X equals -1/3 after I take -2 divided by 6. So there's our zeros. -1/3, -1, -1/3, 1/2, and 2. So f of x then can be factored this way. X plus 1/3, x minus 1/2, x plus 1, I know I'm all over the place here, and x minus 2 would be our factors. Now, we will look at 7 with our next case using some complex zeros. But this is the first